Hello, today we're going to implement a multi-class classification and we're going to use the iris classical dataset. Uh, Important note is that we're not allowed to import the dataset from Keras, so we're just going to use the provided CSV file. First, we're going to import pandas and then save our file into a variable called file name. And while that is running, okay, and we're going to read the content, and then we're going to save it in a variable called iris. Yeah, I forgot to import it. Now I just did it, and let's run it again. Alright, now we're going to show the first 5 rows of our data frame, and this is what it looks like. It has 5 columns, and now our last column is species column. Is made out of strings, and we want to convert them into integers. We're going to numerize them accordingly. In order to do that, we'll get the species column in iris dataset, and in there we're going to map it, and we're going to map the seto cells into 0, versicolor into 1, and virginica into 2. And let's run this as well. And now we're going to check the first 5 rows, and we can see they're now integers. Now we're going to select the first 4 columns of our data frame, and we're going to call it X. In order to do that, we're using the alloc function. We're choosing the first 4 columns, and let's run this. Let me clear all outputs for now. Okay, so yeah, this is what it looks like. First 4 columns, and then we have 150 rows. Now we're going to do the same thing, but we're going to select the last column. In order to do that, we choose the -1. That means it's the last column in our dataset, and this is what it looks like. 150 entries and 1 column. And now we're going to split the data and the label into training and testing segments. We're going to call them xtrain xtest, ytrain, and ytest. And we're going to split the data and the label into training and testing segments. And we're going to keep the size of the test data into 20%. We're going to set the random state into 123. In order to do that, we import the train test split from sklearn, and we put our data in our label. Then we're going to use the train test split function to determine our test size, which is 20%, and our random state is 123. Let's run it. Okay, now we're going to check the first 5 rows. Xtrain head, what it looks like. Xtest, this is what it looks like. Our ytrain and our ytest. Okay, so far so good. Now we're going to check the length of our xtrain and xtest, and we're going to check if the numbers are 120 and 30. Our xtrain shape is 120, what we were looking for, and our xtest shape is 30, which is what we're looking for. Great. Now we're going to convert ytrain and ytest into categorical, and we're going to call them 1 hot train labels and 1 hot test labels respectively. In order to do that, we're going to import to categorical function from Keras library, and then we're going to put them in our test and train labels. We're going to use the categorical function, and let's run it. And once we print their shapes, this is what it should look like. And now we're going to define a sequential model, and it's going to contain 3 dense layers. In the first 2 layers, we're going to use 100 neurons and a ReLU function as an activation function. And in the last layer, we're going to use 3 as the number of output. And the reason why we're using 3 as an number of output is because we have 3 classes: Setosa, Versicolor, and Virginica. We're going to pick an appropriate activation function for the last layer. In order to do that, we're going to import sequential and dense from Keras library, and we're going to define our model as a sequential, and then we're going to add our model 100 heating units first, and our activation function is ReLU, and our input shape is 4. We choose our input shape as 4 because we're dealing with 4 columns at the moment. And our second layer is going to have 100 neurons as well as ReLU activation function. And our last layer has 3 as a number of output, and I chose softmax activation because we're dealing with multiclass classification, and softmax is one of the appropriate models to go for. And let's see the summary of it, and this is what it looks like. We have our layers, dense layer, and then layer 1, layer 2, and we can see our output shape and number of parameters, and then we have the total parameters, trainable parameters, and non-trainable parameters right here. Now we're going to compile our model. We're going to use the RMS prop and appropriate loss function and accuracy for our metrics. So we're going to compile our model with an RMS prop optimizer. I chose categorical cross entropy for our loss function because we're dealing with, again, multi-class classification, and categorical cross entropy is one of the appropriate loss functions for it, and our matrix is accuracy. Let's run this as well. Okay, great. And now we're going to fit our model using we're going to set our epochs to 20 and our batch size to 10. Now we have our history and our model. We're going to fit it in, and we're going to use the X-train and 1 hot train labels. And we have 20 epochs, and our batch size is 10. And we're using X test and 1 hot test labels as our validation data. Let's run this as well. Now it's going to take some time. It's going to run all the epochs, and this is what it looks like. So as we can see, our loss started at a greater, and it started to decrease over epochs, as well as our accuracy started to increase. It also decreases at some point, but it's alright. And then we're going to calculate our result. We're going to evaluate our X test and 1 hot test label, and we're going to see how accurate our model works. And let's run it. And our test accuracy is around 96%, which is good. And now we're going to repeat what we've done in the question 6, and we're going to follow a different approach. In the first and second layer, we're going to use 10 heating units or neurons. We're using ReLU function, and well, our input shape is the same, and still 3 outputs, and activation is softmax. Let's run it, and this is what it looks like. Now we have 193 total parameters, and this is what it looks like. We're going to use the same thing we used for the question 6. We're going to compile this using RMS prop, and the same thing, categorical cross entropy and accuracy for our metrics. Let's run this as well. Okay, now we're going to fit this, what we just did, our model, into 4 epochs and 10 batches. It's the same thing what we did before, so let's run this. This is what it looks like. Very high loss and very low accuracy. And now we're going to calculate our result and evaluate our X test and one hot test labels, and we're going to see how accurate the model works. And as we can see, our test accuracy is around 0.36. Alright, now we have some questions that needs answering and explanation. So first one is how the number of layers or heating units could impact the accuracy of our model. Well, layers and heating units in our neural network model can significantly impact its accuracy. Having more heating units in a layer allows the model to learn more complex representation of the input data, which can lead to better accuracy. However, though, having too many hidden units can result in overfitting, where the model becomes too complex and starts to memorize the training data instead of generalizing to new unseen data. And our second question is, do we always suffer from overfitting? Not always. Overfitting occurs when a model is too complex and learns too much information from the training data. And our last question is, how can we find and manage overfitting? Well, we have an overfitting. We can determine it when the model performs very well on the training data, but it performs very poorly on the validation or test data. We can manage overfitting by using regularization, dropout, and early stopping. And now we're going to use a different approach as we did in question 9, but now this time we're going to change number of layers, hidden units. We're going to change the compile parameters, number of epochs, batch size, whatever we want. And I changed the hidden units, neurons, and I changed the activation function of the first one to sigmoid, and I chose our optimizer as atom, and our epochs is 15 and batch size is 45. Now let's see what it looks like. Let's run this. Alright, now after 15 epochs, this is what it looks like. 1.07 for our loss, and our accuracy is 0.59. Now let's run this, and our test accuracy is around 0.76. Okay, thank you for watching.